All right, so for today's review, we're going to look at all the topics that are on test 8. There are a lot of them. Okay? Yeah.
You do that with what's it called? I was like, you don't get that. You did the chalkboard
With the freshmen after school?
Yeah, after school,
Yeah.
and I was like,
Well, I don't usually do this during class because I usually have the white because the PDF I upload is white anyway. Now, the sections that are involved are as follows. Okay, now the chapter 14 stuff, okay, the chapter 14 stuff is the oldest stuff. So make sure when you're looking at this, you go back and really think about that. Okay, chapter 15 was more recent, and 17 is what we've been doing lately on electric charge. Now, there are several new formulas that are added to this test, and you know what they are, but I'll just write them down so we're all clear. The first, God bless you, the first new formula that we're looking at, okay, was, and I'll go to the next page to start, or I'll scroll down a little bit, start writing this.
Oh, do you know any of my classes?
Oh yeah.
Where it's like, I was wondering
Like nearsighted versus farsighted? Yeah, that's theoretical stuff, yeah. It's all a possible fair game for it, absolutely.
Swag.
No way.
Yeah. Swag. It's like this like school has.
So you made 5 textbooks.
Did you have to pay for it or is it actually free?
No, look.
That's illegal.
It's like every single chapter.
That's illegal.
is it pirated or what?
You just click like chapter
Every
2.
chapter of what?
The textphysics textbook.
No way.
Wait, yes,
Email me the link. Do you mind?
It's online. It's online.
It's the same thing, guys. It's our textbook. It's just showing it. That's awesome. Email me the link, Max.
I've
All right.
been through a lot these days.
So the formula that we started with in chapter 14 that we used this in an earlier chapter as well. We used V equals lambda omega when we were talking about frequency and wavelength. Now, in chapter 14, we were specifically talking about electromagnetic waves, okay, EM waves. So because of that, we replaced V with C, okay? So you're not going to see that formula on the test. You're not going to see C equals lambda omega. You're going to see this formula down here. But what you need to know, okay, what you need to really know is that when you see V equals lambda omega, if it's an EM wave, all EM waves travel at the speed of light. So immediately replace this and make the equation look like this. Okay? So that's what you need to know to do. Now, the next thing, we need to all listen, guys. We need to listen, focus. The next thing that we're going to look at here, okay, is our value of n. Remember, n was derived using this formula. N being the index of refraction in chapter 15. Okay? So any index of refraction for any material can be determined if you take the quotient of the speed of light and the velocity of the wave in that material. So for example, if you want to know what the n value is for glass, which happens to be 1.5, okay, you can say, all right, take the speed of light and divide it by the speed of light in glass. And if you do that, you'll get 1.5. If you take the speed of light, and then you take the speed of light in water and divide them, you'll get n for water, which is 1.33, and so forth and so on. Okay? So that's where n came from. This is a formula that's given. We haven't done much math with this, but this will come up maybe conceptually as far as what's happening here. Okay, understanding what's going on. And we spoke about this in class, and it's in your notes. Okay? It's in your notes. Jeff?
Okay, 2 things. You can consider C is just speed of light in air, right?
Correct. Or vacuum or air. We're saying air is the same for now.
In the problem set,
Yep.
I remember it said all massless particles including EM waves. So it's actually all particles when they are traveling in vacuums travel at the speed of light.
No. Only EM waves travel the speed of light. You must have misread it.
All
Absolutely.
massless particles.
Well, again, Jeff, massless particles are things like EM waves. Like if you're thinking about like a baseball, it has mass, right?
Oh, yeah.
So like you can't think about something like that in a vacuum. That would not. So like electrons or photons and different things that are massless, but that gets into a little bit trickier. Just for the sake of this, EM waves travel at the speed of light. But your statement is good. I like that. All massless, but don't assume that that's any particle, okay? Because most particles do have mass. Index of refraction.
Wait, and you find that by doing...
The speed of light over the speed of whatever it is in that material. Speed of light in that material.
So velocity is just it's the speed of the object times the of that material. Refraction.
Speed of light in air or a vacuum, the speed of light when it hits the material you're looking at. So in glass, the speed of light reduces a lot. So this is going to be some number smaller than C. We talked about how this always has to be greater than 1, okay? Because C is always bigger than anything else. The next formula was Snell's law.
Will C always be greater than V?
Always. That's in your notes. V.
Faster than
Okay? Remember, nothing can travel faster than the speed of light. Okay? And whenever it comes from air, it always slows down. Exactly.
light's just the fastest
Okay.
thing in the world.
Now, Snell's law. You need to be able to solve for any of the variables. So if you're solving for Ni, you just divide by sine theta I. That's easy. If you're solving for Nr, you just divide by sine theta R. That's easy. But when you're solving for theta I and theta R, you need to get rid of the sign afterward. What do? Raise your hand to get rid of sine.
You drew a sign to the -1.
Exactly.
And then on the calculator, it's just you do separate sign.
Very good. That's it. So if you wanted to solve for theta I here, you would divide by Ni, like so, and then you would take the sine inverse to get rid of the sign there. So theta I would be the sine inverse of that entire quotient over there.
And it could be, well,
Okay?
you could do that first and then just multiply those.
Yeah, so you could not multiply, be careful, remember? You can do this first and get a decimal and take the sine inverse of that. It's not a multiplication operation. You're going to learn more about this year in Algebra 2.
Just plug in sine inverse and then put that.
And then put the number in. Yep, exactly. It's like a square root function. You know when you take a square root, it opens parentheses? Same thing in the calculator. Jack.
Well, I'll ask when we're done.
Yes, you can plug in numbers, are you going to say?
Oh no, I was just wondering when we're done with the formulas if we could have like a calculator review how to
Sure.
calculate that.
Yep. All right. The next formula was for the critical angle. Critical angle was given as theta C equals sine inverse of NR over NI. Okay, NR over NI. Now, remember the hint I taught you guys. If you mix up NR and NI by accident, you mix them up, make believe, for some reason, you're going to get an error. It's not going to work. Okay? Because remember that NR,
Has to be less than
NR has to be less than NI. Okay? This has to be a decimal. Not imaginary, it's just not in the domain of the sine function. So it will give you an error. It'll say not in domain or what will it say actually? I wonder. I don't know. Type in sine inverse. What is it? Error domain. There we go. I knew I had to do the domain, but I forget what the exact coding of the error is. It's because the sine wave, its max amplitude and min amplitude is 1 and -1. So the inverse is looking for that location, and it can't find it. But it's hard for me to explain that to you right now. It just turn on its own?
Oh
It was weird.
It's weird.
Because you haven't seen it yet in Algebra 2, okay? But you're going to study that and it'll make more sense. But for now, know that when you do sine inverse, this quotient needs to be a decimal value.
And then if the critical angle is less than the delta I or theta I, then it's internally.
Yeah, I was gonna ask.
Greater than. So, if the critical angle is less than the theta I, sure, yeah. Then here's how I think about it. If your incident angle exceeds the critical angle, it's totally internally reflected. Again, if the theta I exceeds the critical angle is like your limit. If you go above the critical angle, you have total internal reflection. Okay, so when theta I is greater than theta C, there's total internal reflection.
When you do the sine, you just go like, if I have like 6 sine, you just do second sine.
We moved on while we were doing
second
your
sine.
little shenanigans.
Yeah, you do like.
Last formula.
Isn't the brightest formula on it?
The brightness is not a formula, it's a relationship.
I know.
Okay? We can go over it, sure, but it's not a formula. It's not going to be given. It's not given. Sure. This is from yesterday. This should be fresh in your mind. Okay? And from your problem sets last night.
FG is also
Okay.
on it too, right?
FG is already on the formula sheet. That's on there from earlier.
It's on the test.
It's free game. I'm not telling you it's not or not, but it's fair game. Every topic we study is always fair game. Remember, KC is a constant. That'll be given also on the test. Okay? Q1 of the charges. 9 times 10 to the 9.
Negative 9. 9
No.
times 10 to the negative 9.
No, 9 times 10 to the positive 9.
That's speed of light.
It's alright. Don't worry, guys, if that's the only mistake on there. It won't kill you. It's 10 to the positive 9. Positive 9.
Well, you did 1.6.
Yeah, I did 1.6.
So, I automatically fixed you, so you can stop.
Either way, it's 9 times 10 to the 9. Okay? Alright, let's get into the actual test now, okay?
Come on, Fernando. Shut up, Jody.
Whoa.
Wait, what is this? This is electric force. Force electric.
Electric force. Yep. Alright, so, things you should know. Very conceptual, so I'm going to go through just general things and we'll talk. Okay, very little math if you've noticed. Okay, first. Come on. New page. First thing. We talked about surfaces being specular and diffuse. What is the difference? Olivier.
Specular, like, it's a perfect rebound, and diffuse is like all like rough.
Good, and the surface is rough for diffuse and it is smooth for specular. Okay? Remember, specular, smooth. They're both S's. Okay? Specular, smooth. Specular, smooth. Diffuse is the rough surface where the angles come off at random angles. Now, if we have incoming rays on a specular surface and look like this, what do the outgoing rays look like
Parallel,
in the
refractive.
reflected angle? Yeah. So they're going to look like this. Okay? That's an example of specular. Remember that the incident angle, theta I, right here, is equal to the reflected angle, theta prime. The incident angle here is equal to the reflected angle here. And I'm using my hand to show you. That's one of our laws.
Why'd you call it theta prime instead of theta r?
Because theta r is the refracted angle. Remember that one when it comes through? Okay? Stash.
Don't all surfaces have both of specular and
Do surfaces have both?
don't all surfaces have both?
Sure, absolutely. But remember what we talked about? We talked about modeling things, right? Making assumptions. So like, for example, when you see a mirror, you assume it to be specular. Even though on a microscopic level, everything is diffuse. But on a macroscopic level, it's specular because the EM waves are not small enough that they're going to get deviated by the small deviation in the surface. EM waves, the wavelengths are big enough so that it'll come off at a rebounded angle that is the same as the incoming. Okay?
What if like a material is perfectly smooth?
Uh-huh.
It doesn't reflect. If like that.
Yeah, that's
wood
what I
is
was gonna say.
Perfectly smooth.
This is perfectly smooth. I can't see more.
No, this reflects.
No.
It reflects a little bit. But if that piece of wood is perfectly smooth, like what would that mean? And it doesn't reflect.
It still is reflecting. It still is reflecting. Because you're seeing... But guys, think about it for a second. This wall, make believe this wall is perfectly smooth. Aren't you seeing blue?
Yeah.
So isn't blue being reflected? You're not necessarily seeing an image reflected like a mirror would, but you are seeing the blue being reflected off.
What about this paper?
Like a piece of paper? Well, a piece of paper...
No. This paper is actually really rough.
Yeah, a piece of paper is actually very, very rough. Yeah, it's not smooth. Smooth, you want to think of? Think about something that would produce a glare. And we'll say that it is smooth. To make an assumption. I'm not going to give you... Listen, guys. I'm not going to give you questions that are somewhat ambiguous. on the test. I know that one of your problem sets, a few you didn't know, there was like one with the mercury column, was that diffuse, was it specular?
Well, I looked at my
Okay.
thermometer in my wall and I saw that.
Thank you.
Okay, well that's good. Okay. But generally speaking, I'm not going to go crazy with that answer on the problem set, so you probably won't lose points on that, and I'll write a little note. But when it comes to the test, know the difference between them, okay? Between the terms diffuse and specular and what they are. And I'll ask you maybe to give examples instead of me giving examples. So give me an example of a surface that is specular. Give me an example of a surface that is diffuse. And you need to be able to come up with that for sure. That is very easy to do. But I won't necessarily give you any surface and say, determine if it's specular or diffuse if it's a little bit ambiguous, okay? Paul?
That illustration on the board, that is
Specular. Diffuse would be this. All of them coming in parallel, and then the rebound array is coming off at random angles. Okay?
So that means that
Hold on, Jack was next, sorry.
like a unrippled pond is spectrum,
Smooth.
right? Yeah, smooth.
Unrippled.
Are you gonna ask questions about like the retina in the eye? Like how this is kind of like how
Right in the eye had to do with converging and diverging lenses, though. Not specular and diffuse. Reflection. Different. Okay? We'll get there.
What section is this? It's 14 too.
I don't know. It's still 14. Forget which section it is exactly, but it's 14. Yep. Absolutely. All right. Jeff, you have a question? Unequal.
That's if you're good in math.
All right. Here's what you should know. Two things for this next part. When a wave travels from one medium to the other, you should know whether it bends toward the normal or away from the normal without doing any math. Just simply based on the index of refractions, or indices of refraction, or whether or not the light ray speeds up or slows down. So for example, when a light wave goes from air into any other medium, it always bends toward the normal because the wave slows down. So when a wave slows down, it bends toward the normal. When a wave speeds up, it bends away from the normal.
Wait, speed effects?
Okay? Absolutely, and we've made this discussion already. And that is also what affects the n value. So if the n value goes from a lower n to a higher n, it bends toward the normal. When a wave goes from a higher n to lower n, it bends away from the normal.
Okay, so higher velocity means closer to the normal, and lower velocity means...
You're not making your statement correct. Restate it. Fernando, you're making people confused. If it goes from a low velocity to a high velocity, that's what you have to say. You can't say high velocity. It doesn't mean anything. It's the change that's important. So low velocity to high velocity, it bends away. High velocity to low velocity, it bends toward. Okay? It's the relationship that you're looking at. Guys, come on. You need to write stuff. High velocity to low velocity, toward the normal. Low velocity to high velocity, away from the normal. And these are in your notes. We've discussed all of this already. Okay? For n values, lower n to a higher n, it bends toward the normal. Higher n to a lower n, it bends away from the normal. Always think about air as the example. Always think about air as the example.
How are we supposed to know on the test? Let's say you give us glycerin and like.
You'll be given the n values. You'll be told it speeds up or slows down. You'll be given the information needed to determine what happens. All right. How does an object get charged? Does it lose or gain electrons, or does it lose or gain protons? What happens? Who wants to tell us? Good. Remember, electrons are the only things that can move. So if an object gets a positive charge, it must have lost electrons because electrons are negatively charged. Okay, it cannot lose or gain protons or neutrons. I mean, it can, which is a little different though. That's fission and fusion, not charging. Okay? Know the difference between like signs and opposite signs, and have to do with repelling and attracting. Know the processes. Ready? Know induction. Know polarization. Know those two and how they work. Okay? Know the difference between conductors, semiconductors, superconductors, and insulators. Okay? This is all of section 14.1 that I'm talking about right now. 17.1. Wow. Sorry, 17.1. I'm sorry. Okay, so again, you need to know polarization, induction for sure. The difference between the insulator and conductor, superconductor, and semiconductors.
Difference between conductor and superconductor.
Just generally the difference between the conductors, the three of them, semi, regular conductor, and superconductor, and what an insulator is. Know about light and colors. When you see red, what's happening?
It's absorbing every color.
It's absorbing everything but red. When you see white, it's doing what? One person raised their hand. When you see white, what's happening?
It's not absorbing any color.
Good. When you see black, what is happening?
It's absorbing everything.
Good.
Black hole.
Know the reason, listen. Know the reason why you wear sunglasses that are polarized and what polarization actually does. Okay? Not polarization in the terms of electric forces, but polarization with light waves. What does it say in your notes, Jeff? Read it to us. What is polarization for light waves?
Light waves? What section is that?
14 through 2 and 4, I think.
It's the presence of a charge.
No, that's 17. That's the different polarization.
That's the induction conductor.
Yep. Look in chapter 14, section 2 or 4. You'll see polarization. We talked about polarizing light. Joey.
In the presence of a charged object and insulators.
Other one, Joey. That's 17. Go back to chapter 14. Molly.
So the alignment of EM waves in such a way that the vibrations of the electric fields are parallel.
Yes, it has to do with changing the electric fields so that they're parallel to the motion of the wave. And that causes a reduction in the glare. Okay? Remember that we use polarized things like sunglasses to reduce glare.
Could you repeat that one more time, the polarization?
It has to do with realigning the electric field, right? Or electric field waves, I said. I want to make sure. EM waves. So that they are parallel to the motion of the wave and it reduces the glare. Okay? Because glare is existing because of the orientation of the EM waves. How does a prism work and how is a rainbow produced? Olivier.
Well, when the light travels through the prism, it actually breaks the light apart.
Good. Why? How? What process? Yeah, refraction. It's bending it into its different wavelengths, showing the colors. How does that affect a rainbow? How is that analogous to a rainbow? What's happening with a rainbow?
It's like refracting off all the raindrops?
Yes, it's refracting through the raindrops, right? So those raindrops are able to bend the light waves.
But it's also reflected with the sun. That's why.
Sure, there is reflection also there, yeah. There's definitely reflection involved.
In such a way that the vibrations of the electric fields are parallel.
Please understand how nearsightedness and farsightedness is corrected. And how diverging, or what happens with a diverging versus a converging lens. And if you're explaining, don't say a converging lens converges and a diverging lens diverges. That doesn't help me. Okay? Do not say that. You're not going to get credit for that statement. Okay?
We draw this.
All those part twos, you can draw pictures. You can always do that stuff. Yeah.
Wait,
Remember,
for what?
pictures, equations, all that stuff. For lenses.
Oh.
Lenses.
Can we draw a picture?
Know the idea of fiber optics. I'm testing you on almost everything that we've covered. I'm not going to lie. Everything that's been covered is going to be on there.
Oh, thanks for
Okay? So just keep that in mind.
Good tip.
Know how fiber optics
It's really
works?
helpful, Mr. Howell.
You got him for that.
Know how fiber optics works?
Fiber optics. I was trying to say Vios.
That's just like the light bouncing inside these like small tubes.
Yep. It's in your notes. It's on the notes in section 14.4.
Okay.
Or no, 15.4. Or 15. 15.
So wait, Mr. Howell, if we look through the notes and like watch the videos for stuff we don't understand,
You should
we'll
study your notes. Look over your the problem set if you made a copy, like I was saying, or those problem sets. And then maybe look at the labs and have the ideas of how the labs work. Yeah, those are like same as every test. Notes, labs, problem sets. Let's see. Let's do some example math problems. Example math problems to look at.
Are we going to be testing on radio waves, microwaves, waves?
Okay. For the EM spectrum, can you stop talking, please? Shh. For the EM spectrum, you don't need to memorize the wavelengths and stuff. You don't ever have to do that. But you need to know what's happening, how the wavelength changes throughout the EM spectrum, how the frequency changes, how different waves have different lengths. So radio waves are different from gamma waves, and they have different applications. Okay, and we talked about those in class. Let's look at an example, though, now of our math problems. I'm going to tell you exactly the kind of problems to expect. So you're going to have... Understand what?
We understand the math problems.
Then we can stop. We're done.
You understand
We're done with reviewing everything else.
We didn't review, you just told us what to know.
Okay, so let me go over the math problems and maybe I'll take questions. Jack, if you have a specific question, ask me in office hours today about something you don't get. Okay? So, you're going to have a problem that will definitely involve your frequency and wavelengths. Okay? You have a problem like that. And we did one of those in your notes. You'll have a problem that will involve refraction and Snell's law.
Do we not have a critical angle?
Okay? Critical angle will not come up as a math problem, but you need to know what it is for sure. It's definitely on the test several times. Okay, the critical angle might not come up as a math problem though. Well, in the problem, it depends. If it's an EM wave, yes. If it's not an EM wave, then you have to use the velocity given. Right? You should know how to do problems with FE equals KC Q1 Q2 over R squared. I'll tell you now there's going to be two of those. Okay? And you're going to have to think about what you're solving for. So if you're just asked to find the force and compare it to the force of gravity like we did, that's one thing. If you're asked to find the distance between them, you have to solve for R. If you're told that the point charges are identical, then this becomes Q times Q, which is Q squared. You have to solve for Q. If you're told that the point charge, this one, you should know that an electron is given as that value E, and we wrote that in our notes. So if I tell you there's an electron and a proton, okay, the value or the charge of an electron is given. It's one of our constants. It's on the test. The constant for an electron, if you remember, is negative 1.6 times 10 to the negative 19 coulombs. That's an electron. A proton is 1.6 times 10 to the negative 19 coulombs. Okay? The value E is given as a constant on the test.
That's E stands for electron, right?
Okay? E stands for fundamental unit charge. An electron is negative E. A proton is positive E. If you have a nucleus, and let's say the nucleus has 20 protons, then you have how many E's? 20 E's. So if you have a nucleus with 20 protons, then you would have to multiply this by 20, and you'll get the total charge of the nucleus. Okay? Again, this is an electron. This is a proton. But if you have, like, say 7 electrons, you have 7 of these charges right here. Okay? That means you have 7 of these charges. So you'd have to multiply this by 7. Don't worry about this, obviously. It's the scientific part. Multiply this by 7. If you have 35 protons and you have 14 electrons and you want to find the charge or the force between them overall, you'd have 35 of these and 14 of these. So you have to multiply them accordingly.
What's mu again?
Okay? Mu stands for times 10 to the negative 6. Jack.
Kc is a constant of 9 times 10 to the 9th, right?
Correct.
Okay.
Correct. R is the distance between the centers of the two charged particles.
Mu is that's going to be given on the test.
You should know these guys, but I'll give them to you. Okay? And you should really know them by now.
G for giga.
G is for giga, 10 to the 9. M is for mega, 10 to the 6. Mu is for micro, 10 to the negative 6. And there were others, like milli, little m, is 10 to the negative 3rd. Kilo is 10 to the positive 3rd. Okay? These are all of our prefixes. Mu is micro. Micro. Yeah.
Why? What's
No, it's because you got.
The term.
I did that on my third floor.
I bridged that.
I know not to sit on that.
It never happened.
I ate a heavy breakfast today.
We're recording.
That's all right.
You edited that out.
The mu value is actually called micro. Okay, it's actually called micro, but the symbol is called mu. That's why I've been saying mu there. Okay, so like a microcoulomb is mu c. It means microcoulomb. It's a coulomb times 10 to the negative 6. Okay, that's the ones we did in class. Other general questions? Dan, go back a slide. Sure. Jeff.
When we're doing a problem like that on the test for force of electron or electricity or whatever, when we're trying to find, because in the problem set there was like a problem that they didn't give you the electrons, the Q,
Okay.
Q2.
They said what?
Uh,
How many electrons are transferred in the process?
no, I
Is that
think
one
it
of
was
them?
just like, no, but is it possible that we just use that they're not going to give that to you, but you use automatically negative 1.6 and a positive 1.6?
Well, if you're guys, if a problem says that there's an electron and 12 protons, that means one charge is the charge of an electron. Negative 1.6 times 10 to the negative 19. The other charge, and say there's 10 protons, is 10 times 1.6 times 10 to the negative 19 for the proton charge.
So that'd just be 10, but 10 times 1.6, then that number times 10 to the, okay, not 4.
Correct, correct.
Can we go over that thing where you're talking about the low to high velocity and high to low velocity? Sample problem?
A sample problem? If an object or if a light wave goes from water to air, what happens to it? Does it bend towards the normal? Does it bend away? Does it not? What happens?
Since it's going from high velocity to a low velocity.
I said water to air.
Oh.
That's low velocity to high. Air is always the fastest velocity.
Oh yeah. Low to velocity to high velocity, it bends towards the normal. Away from the normal.
Away from the normal.
You know what, Jeff? Like, SAS?
Away from the normal. You can always check by using mathematical values. You could let n equal 1.3 for water, let n equal 1 for air, pick a random angle, and then find the refracted angle, and you'll see that the refracted angle is greater than the incident angle. So that always works, Fernando. You can always check.
Is that the same thing as when you say, like, if Ni is greater than
Yeah,
R, then
it's the same
Li,
relationship.
and then theta I
They're like flipped, really.
is less than theta R?
For a fast medium, the n is low. For a slow medium, the n is high.
Take that top there.
Yeah, n is greater, yep. Next.
Oh yeah, when there's a question that said that it's like when a conductor is charged by an induction, you use surface charge on the conductor's opposite, or like it has to go as opposite or the same. Like similar to the.
Repeat one more time.
When a conductor is charged by an induction, and use surface charge is the opposite or the same as the object inducing surface.
All right, let's look at induction then to answer this question. So for induction, if you remember, for induction, what we have is we have a charged rod of some sort, and then we have some conductor over here that has positives and negatives all over it, right? It's neutral. Now, when you bring the rod near the conductor, what happens to all those charges? What do they do?
The opposites go to the surface.
Yes, the opposites come to the surface.
No, that's where the line.
That's what happens, right? Then we attach what's called a grounding. We ground it, or we connect it to the ground. And what happens is when you connect it to the ground, all of the charges that aren't held there by this rod, also all these extra positive charges, flow through the ground, or flow into the ground. So all of these charges, Max, right here, all these, they flow into the ground. So now they're gone. Then you remove the grounding. So now you have this.
Wait, it's grounded, or is it not grounded?
It's grounded, so then they move out into the ground. Then you remove the grounding, and you're left with a conductor with all negative charges all over it. And then when you remove this rod here, you're left with a conductor with all negative charges on the surface until you remove the rod, and then it's just all negative charges. So you have
What's a real life example
of something you would use for induction. It occurs a lot in motors. Okay, it has to do with motors. For now, know the process. We haven't gotten to any of those yet. We're going to get to induction when we look at
I
circuits.
was thinking with the lightning rod.
Lightning rod is not induction. Lightning rod is just, there's a lot of electrons that hit the metal in the conductor, they flow through the metal into the ground, and they pass through. But it's not induction. Okay? Jeff?
You said at the last final step on these, there's all negative at the first surface left, but then.
And then when you remove the rod, the negatives just spread out evenly. It's not touching. It's never touching. It's never touching. If it's touching, then it would be charging by contact.
And here we go.
That's like me walking up to you and giving you a static charge. Say again? Yeah, that would be a contact example, but because this is a field force, the field force is implying that there's no contact.
Okay, so then the negative, when you remove it, then what happens?
Alright, so you remove the grounding, and it looks like this, right here, where all the negatives are on the surface. But then when you remove the rod, the negatives just spread out among the conductor. Okay? Other questions? Other questions? Just as a reminder, those of you on iPads, make sure you're only working on your notes. Okay, make sure you're only working on your notes. Which one?
Number 2.
Okay, so
I just don't know why it would be I get what you just said
Low end to high end.
it's
So-
just saying it in different
That's all. It's saying the same thing we just did here, Max. You put a positively charged rod near it. It pulls the negatives to the surface. You ground it. The positives flow out. When you remove the rod, what's left? All negatives. So what's the signs?
the opposite.
for nearsighted, it hits the retina too close, right before the retina.
For nearsighted, listen up. Listen up. For nearsighted, look in your notes for nearsighted. When you're nearsighted, you can see things that are near to you, right? When did it converge? Did it converge before or after the retina? Look in your notes. Don't just answer. I want you guys to check. You have these in there. So I want you to answer these questions yourselves. Look at your diagram for nearsightedness. Look at your diagram for nearsightedness.
Earlier.
So what kind of a lens do you have to use for nearsightedness? Yeah, diverging lens. So it spreads out the waves a little bit so they converge a little later. For farsightedness, it converges too far or far past the retina. So you use a converging lens to get the waves to converge earlier. Okay? To converge earlier. You don't need to know the terms myopia and hyperopia. Okay? Just know nearsighted and farsighted.
On a separate topic, they just found glasses that correct color blindness.
Did they?
Yeah,
When did this happen?
2 days.
Or they just invented? They didn't find them.
Don't
Or, yeah,
no,
that's-
he doesn't have that. He just has it to protect from the sun.
So they're probably highly polarized.
Yeah, oh yeah.
Because he gets a lot of glare on the ground. I know. He told
It
me.
was
We were talking about that
MIT students or something. Somebody
So they're able to. What are they able to do?
I'm not.
Because it's the cones in your eyes that are receptors of colors.
Yeah, no, I posted it on Donald Wall.
Ah,
You can
okay.
see now.
Stash.
I don't think I've actually read the article. It's like it intensifies certain colors that are not actually in school lists. So I'd say if you they're less sensitive to green light, it does intensify the green light. But it's
Okay. But it's not replacing those cones that are missing.
Wait, you just said that nearsighted converges before the retina.
So you need to use diverging lens
And then farsighted
after the retina. So you use a converging lens to get it to converge earlier.
converging is for both of them.
Well, everything converges, but it's depending on which lens you're going to use.
Example about retreat after that you want to